Hey there, and welcome to the Sleepless Scientist. Tonight, we're embarking on a journey into one of life's most profound mysteries, consciousness. What does it mean to truly be? How do we experience the world, and what is that inner voice that makes us us? This isn't just a story about scientific facts. It's an exploration of human curiosity itself, a quiet quest spanning millennia. We'll delve into the whispers of ancient philosophers and the hum of modern labs, all trying to understand the elusive I. If this journey sparks your own curiosity, please consider liking this video and subscribing to the channel. It helps us continue these explorations. Now, let's travel back in time to where these questions first began to echo across the ancient world. Our story truly begins not in a lab, but in the sun-drenched plazas of ancient Greece. Here, thinkers like Plato wrestled with fundamental questions of existence. Imagine a group of students gathered, listening intently to his words. Plato introduced the famous allegory of the cave. He asked us to imagine prisoners chained, facing a wall, seeing only shadows cast by a fire behind them. For them, these shadows were reality, the only world they knew. This thought experiment wasn't just a story, it was a profound inquiry into perception. What if our everyday reality is just a collection of shadows? What if there's a deeper truth, a more fundamental reality that we are missing? Plato's idea suggested that our senses might deceive us. The mind, he proposed, could access a realm of perfect forms, true knowledge beyond the changing world of appearances. This was an early attempt to separate mind from the material world. This notion planted a seed, the idea that our inner experience, our consciousness, might be distinct from the physical body. It was a radical thought, challenging the intuitive connection between what we see and what truly is. Following Plato came Aristotle, a student who respectfully charted his own course. Aristotle approached the psyche, often translated as soul or mind, with a more empirical, grounded perspective. For Aristotle, the psyche wasn't a separate entity trapped in the body, but rather the form of the body. It was what made a living thing alive, its organizing principle, its capacity for sensation, thought, and growth. He believed the mind couldn't exist without the body, just as the shape of an axe couldn't exist without the axe itself. The two were intrinsically linked, a single, functioning unit. This offered a very different lens through which to view consciousness. It wasn't about escaping a false reality, but about understanding the intricate functions that made living beings perceive and act within their world. Both Plato and Aristotle, despite their differing views, laid the groundwork. They showed that asking what is consciousness was not just a philosophical parlor game, but a fundamental inquiry into what it means to be alive. Centuries passed and the conversation evolved. Fast forward to the Renaissance, a time of rebirth and radical new ideas. Here, a French philosopher named René Descartes picked up the thread, but with a new kind of rigor. Descartes was a man seeking certainty. He famously doubted everything he could, stripping away all assumptions until he found something undeniable. This methodical doubt led him to a profound realization. He realized that even if he doubted everything, he could not doubt that he was doubting, and if he was doubting, he must be thinking, and if he was thinking, he must exist. This led to his iconic declaration, cogito ergo sum, I think, therefore I am. It was a bedrock of certainty, a starting point for understanding existence, rooted in the very act of conscious thought. Descartes then proposed mind-body dualism. He argued that the mind or consciousness was a non-physical substance, res cogitans, or thinking substance, entirely distinct from the physical body, res extensa, or extended substance. This dualism suggested that while the body was a complex machine following physical laws, the mind was something different, something capable of free will and subjective experience. But how did they interact? Descartes famously suggested the pineal gland in the brain as the point of interaction, a tiny bridge between the two realms. This idea, while later disproven, highlighted the challenge of reconciling the physical and the mental. From Plato's shadows to Aristotle's forms and then to Descartes' thinking substance, each era, each mind added another layer to the mystery. They were all grappling with the first whisper of consciousness. They were asking, what is this subjective I that perceives, feels, and thinks? This inner world unique to each of us, yet universally present in every conscious being. It's a question that resonates even today. The early philosophers gave us the language and the initial frameworks. They showed us that the very act of questioning our existence is a part of what defines it. It's like the quiet dawn breaking, revealing the outline of a vast landscape. Their inquiries, though ancient, echo in the most cutting-edge neuroscience labs. The questions they posed are still at the heart of our modern scientific quest to understand the brain and the mind. In our next chapter, we'll move beyond these foundational ideas and into the age of scientific inquiry, where tools and experiments began to peer directly into the machine of the brain, seeking the elusive seat of consciousness. Until then, keep wondering. The philosophers had laid a foundation, sketching the outlines of the mind. But as the 17th century gave way to the 18th and 19th, a new kind of inquiry began. The focus shifted from abstract thought to the tangible, the physical organ beneath the skull, the brain. This was an era of intense anatomical exploration. Scientists, driven by a quiet, persistent curiosity, began to meticulously dissect and examine the human body. They sought to understand its intricate machinery, piece by painstaking piece. The brain, once seen as an inscrutable black box or a mere vessel for the soul, was now becoming an object of direct scientific scrutiny. Its physical form, its texture, its complex folds and convolutions slowly emerged into clearer view. Early dissections were often crude, limited by the tools and knowledge of the time. Yet with each careful incision, a new layer of complexity was revealed. The brain was not a simple, uniform mass, but a densely packed network of structures. Imagine the early anatomists, their hands steady, their eyes keen, as they traced the delicate pathways. They were like cartographers mapping an unknown continent, charting its mountains and valleys, its rivers and forests for the very first time. The sheer intricacy was astounding. They saw the gray matter, the seat of thought, and the white matter, the vast communication lines connecting everything. It was a silent, complex landscape waiting to be understood. But merely describing the brain's physical appearance wasn't enough. The deeper question lingered: did different parts of this magnificent organ perform different functions? Could thought, memory, and emotion be localized to specific regions? Into this evolving understanding stepped Franz Joseph Gall, a German physician in the late 18th century. He proposed a bold, even audacious, idea: phrenology. Gall believed that specific mental faculties like benevolence, combativeness, or memory were located in distinct areas of the brain. He further theorized that the size of these areas would correspond to the prominence of that trait in an individual. And here was the controversial leap. Gall thought that the underlying brain regions would subtly affect the shape of the skull. Therefore, by feeling the bumps and depressions on a person's head, one could discern their character and abilities. Phrenology became immensely popular, a parlor game and a serious scientific pursuit for some. It offered a seemingly direct window into the mind, a way to map the inner landscape without invasive methods. However, despite its widespread appeal, phrenology faced significant scientific skepticism. Its methods were anecdotal, its correlations often imagined, and its fundamental premise about skull shape proved incorrect. Yet Gall's flawed theory held a crucial, enduring insight. He was among the first to seriously propose that the brain was not a homogeneous blob, but a collection of specialized parts, each with its own role. This idea of localization of function was revolutionary. It shifted the quest for consciousness from a single, elusive seat to a distributed, interconnected system, much like a grand orchestra where each instrument plays a specific part. The true breakthrough in localization came with clinical observations. In the mid-19th century, French physician Paul Broca encountered a patient who could understand language but could only utter a single syllable, tan. After the patient's death, Broca performed an autopsy. He discovered a lesion, a damaged area, in a very specific part of the left frontal lobe of the brain. This area, now known as Broca's area, was directly linked to the production of speech. Broca's discovery was groundbreaking. It provided concrete, empirical evidence that a complex cognitive function like language could be localized to a precise region of the brain. The orchestra was beginning to reveal its sections. A few years later, German neurologist Karl Wernicke identified another crucial language center. His patients could speak fluently, but their words were often nonsensical and they struggled to understand spoken language. Wernicke found damage in a different region in the temporal lobe, now called Wernicke's area. This discovery solidified the idea that language comprehension and production, though related, were distinct functions handled by different brain regions. These findings were profound. They moved the study of the mind from abstract philosophy to observable neuroanatomy. They showed that our thoughts, our words, our very understanding of the world were woven into the physical fabric of the brain. The brain was no longer a mysterious, undifferentiated mass. It was an incredibly intricate biological machine, like a vast, ancient forest slowly revealing its interconnected paths, each leading to a different grove of thought or feeling. Each discovery, from the rough outlines of early anatomists to the precise mapping of language centers, added another layer to the understanding of this most complex organ. The brain was a tapestry woven with countless threads of function. Yet, even with these incredible insights, the hard problem of consciousness remained. How did these localized functions, these intricate electrical and chemical signals, give rise to the subjective experience of seeing red or feeling joy? The brain's grand orchestra had been partially mapped. We knew some of the instruments and where they sat, but how did their individual sounds merge into the rich, unified symphony of conscious experience? That was the next great question. The journey into the mind was just beginning to delve into its physical home. As the 19th century closed, the stage was set for an even deeper dive, using new technologies to peer into the living brain and observe its activity in real time. We were about to enter a new era of exploration. As the 19th century gave way to the 20th, the focus on the brain's physical architecture broadened. Scientists began to recognize that consciousness wasn't just about what was active, but also about what lay beneath the surface, influencing our waking thoughts. It was a shift from mapping the visible to exploring the unseen currents of the mind. In Vienna, a quiet revolution was brewing. Sigmund Freud, a neurologist, began to listen intently to his patients, not just to their conscious complaints, but to the subtle slips of the tongue, the recurring dreams, and the unexplained anxieties that hinted at deeper truths. Freud proposed the existence of the unconscious mind, a vast reservoir of thoughts, memories, and desires that lay outside our immediate awareness. He suggested this hidden realm profoundly shaped our conscious perceptions, emotions, and behaviors, like a submerged iceberg guiding a ship. This was a radical idea. It challenged the notion that we were fully rational beings, masters of our own minds. Instead, it suggested that much of what drove us operated beyond our conscious control, a silent, powerful force. Freud's work, though controversial, opened a new frontier. It forced psychology to consider the dynamic nature of consciousness, acknowledging that our inner experience was far more complex and layered than previously imagined, with hidden motivations and forgotten memories shaping our present. His theories highlighted that consciousness was not a constant, unwavering state, but a shifting landscape, influenced by forces we could not always perceive. It was a profound expansion of what it meant to be aware, including the dark, quiet corners of the mind. Beyond the waking mind, another mystery beckoned: the world of sleep. For centuries, sleep was seen as a passive state, a simple shutdown, but curious minds began to wonder if something more profound was happening in those hours of unconsciousness. Early electroencephalography, or EEG, recordings in the mid-20th century started to reveal the brain's secret life during sleep. Researchers placed electrodes on the scalp, patiently charting the rhythmic electrical activity of the sleeping brain. What they discovered was astonishing. Sleep was not a monolithic state, but a complex series of stages, each characterized by distinct brainwave patterns. The brain, far from being dormant, cycled through different levels of activity. In the 1950s, the discovery of rapid eye movement, REM, sleep by Aserinsky and Klateman provided a critical clue. During REM, sleepers' eyes darted beneath their eyelids and their brain activity resembled wakefulness, despite deep slumber. When awakened from REM sleep, subjects almost invariably reported vivid dreams. This revealed that our conscious experience, in a profoundly altered form, continued even when we were seemingly unconscious. Dreams were not just random noise, but a distinct state of awareness. The discovery of REM and non-REM sleep stages fundamentally changed our understanding of consciousness. It showed that awareness was not simply an on-off switch, but a spectrum with different qualities and intensities, even within the confines of a single night. This spectrum extended further still. For centuries, practices like hypnosis and meditation had hinted at the mind's capacity to enter altered states of perception. Now, science began to explore these phenomena with renewed interest. Studies on hypnosis, though often misunderstood, demonstrated that focused attention and suggestibility could profoundly alter sensory experience. Pain could be reduced, memories recalled, and perceptions shifted, all without physical intervention. Similarly, the ancient practices of meditation, once dismissed as purely spiritual, began to attract scientific scrutiny. Researchers observed changes in brainwave patterns and reported shifts in subjective experience among practitioners. These investigations revealed that the conscious mind was incredibly malleable. Through specific techniques, individuals could intentionally alter their state of awareness, demonstrating a profound capacity for self-regulation and introspection. It was as if the mind possessed many different channels, and through these practices, one could tune into frequencies previously unheard, revealing new layers of inner experience. The boundaries of everyday consciousness began to blur. But perhaps the most dramatic alterations to consciousness came from another source: psychoactive substances. For millennia, various cultures had used plants and compounds to induce profound shifts in perception and thought. As the 20th century progressed, scientists began to systematically study these substances. They observed how compounds interacted with the brain's neurochemistry, leading to intense sensory experiences, altered self-perception, and new ways of thinking. These substances could reshape the landscape of conscious experience, akin to a gentle river flowing into a vast, uncharted lake. The familiar shores of reality receded, and the mind ventured into territories both beautiful and bewildering. Researchers documented vivid hallucinations, profound shifts in emotional states, and radical changes in the sense of time and self. These were not just fleeting sensations, but deep, immersive alterations of the entire conscious field. The study of these altered states, whether induced by sleep, hypnosis, meditation, or substances, provided invaluable insights. It demonstrated the sheer flexibility and diversity of conscious experience, challenging any simple definition. Consciousness was revealed not as a fixed point, but as a dynamic process, constantly shifting, influenced by internal states and external factors. It was a fluid, ever-changing river, sometimes calm, sometimes turbulent, always moving. These explorations of the spectrum of awareness profoundly deepened the mystery. If consciousness could take so many forms, how could we truly understand its fundamental nature? The question of what it is like became even more elusive. The early 20th century had shown us that our inner world was far vaster and more varied than we had dared to imagine. As we moved further into the modern age, new technologies would allow us to peer even deeper, not just into the states of consciousness, but into its very mechanisms, seeking the symphony within the silence. The early 20th century had unveiled a spectrum of awareness, showing consciousness as a fluid, dynamic process. Yet the deeper question remained: how did the brain actually generate this inner world? Scientists, armed with new understanding, began to construct grand theories, attempting to weave together the scattered threads of observation into a coherent tapestry. The challenge was immense. How could a collection of billions of neurons, firing in intricate patterns, give rise to the unified, subjective experience of being? It was like trying to understand a complex machine by only observing its individual gears, without seeing how they all work together. In the mid-20th century, a cognitive revolution was taking hold, shifting focus from pure behavior to the internal mental processes. Among the pioneering thinkers was Bernard Baars, who sought a framework to explain how the brain manages its vast information flow. Baars proposed the global workspace theory, GWT. Imagine consciousness not as a fixed location, but as a kind of broadcasting system within the brain. Information that becomes conscious is made available to many different, otherwise unconscious, specialized processors. Think of it like a theater stage. The spotlight of attention illuminates certain actors, pieces of information, making them visible to the entire audience of the brain. Most of the audience, the specialized processors, work backstage unconsciously until something enters the spotlight. When a piece of information, perhaps the sound of a name or a visual detail, enters this global workspace, it becomes widely accessible. This allows the brain to coordinate its vast resources, integrating sensory input, memory, and plans into a coherent, conscious moment. GWT offered an elegant way to understand how diverse brain areas, each handling specific tasks like vision or language, could contribute to a unified conscious experience. It suggested a mechanism for how we focus our attention and become aware of specific elements of our environment. This theory helped explain why we can only consciously process a limited amount of information at any given time. The spotlight has a finite width, illuminating only what is most relevant or salient, while countless other processes continue in the shadows. Neuroimaging studies like fMRI later sought to identify the neural correlates of this broadcasting. Researchers observed widespread activation across the brain when subjects became consciously aware of a stimulus, lending support to the idea of a global information sharing system. But GWT was not the only compelling theory to emerge. Across the Atlantic, another profound idea began to take shape, one that focused less on information broadcasting and more on the very structure of conscious experience itself. Giulio Tononi and his colleagues developed the Integrated Information Theory, or IT. IIT proposes that consciousness arises from a system's capacity to integrate information. It's about how much information a system has and how irreducibly unified that information is. A key concept in IIT is phi, a mathematical measure of this integrated information. A system with high phi is one where its components are highly interconnected, and the whole is more than the sum of its parts, generating a single, unified experience. For it, consciousness isn't about what information is being processed, but how it's being processed. It's the inherent property of a system to generate a single, unified, and irreducible experience from its many interacting elements. Imagine a mosaic. Each tile is a piece of information, but the conscious experience isn't just seeing individual tiles. It's seeing the complete, coherent image that emerges from their unique arrangement and integration. The whole picture is the conscious part. This theory suggests why a simple light sensor isn't conscious, but a complex brain is. The sensor processes information, but it doesn't integrate it into a unified, irreducible whole in the way a brain does. The difference lies in the organizational complexity. Researchers using IIT explore how phi might be measured in different states of consciousness, from wakefulness to deep sleep, and even in artificial intelligence systems. It offers a quantitative approach to a deeply qualitative phenomenon. Alongside these theories, another powerful idea gained traction: predictive processing. This framework views the brain not as a passive receiver of information, but as an active, constantly generating prediction machine. The brain, according to this view, is always trying to anticipate the next moment. It builds internal models of the world and generates predictions about what it expects to perceive. Our conscious experience is largely a result of these predictions. When sensory input arrives, the brain compares it to its predictions. If there's a mismatch, a prediction error is generated. This error signal is then used to update and refine the internal models, making future predictions more accurate. Consider a scientist constantly refining a model of the universe. Each new observation is compared to the model's predictions. Discrepancies lead to adjustments, gradually building a more accurate and comprehensive understanding. Our brain does this moment by moment. Predictive processing suggests that what we consciously experience isn't raw sensory data, but rather the brain's best guess, its most plausible interpretation of the world, constantly being updated. This applies to perception, action, and even our sense of self. Experiments in this area explore how expectations can profoundly shape our reality. For instance, if you expect to hear a certain sound, your brain might fill in that sound even if it's only faintly present, demonstrating the power of internal models. These theories, global workspace, integrated information, predictive processing, each offer a unique lens through which to view consciousness. No single theory yet provides a complete answer, but each illuminates a crucial facet of this profound mystery. Consciousness, it seems, is less like a single, simple note and more like a complex symphony. Different instruments contribute their unique melodies, rhythms, and harmonies, blending into an intricate, unified whole. Each theory tries to identify a different section of this grand orchestra. These diverse theoretical frameworks have pushed our understanding further, offering glimpses into the how of consciousness. Yet, the why, the hard problem of subjective experience itself, continues to beckon, a quiet, insistent whisper that guides us into the next stage of our journey. The theories of consciousness, from global workspaces to integrated information, offered compelling frameworks for how the brain might organize its activity. Yet the profound mystery of subjective experience, the what it's like of seeing red or feeling joy, continued to elude a full explanation. The philosophical questions still echoed, urging scientists to look deeper. To bridge this gap, a new set of tools emerged in the late 20th century. These technologies allowed researchers to peer into the living brain, not just its structure, but its dynamic activity in real time. It was like finally being able to see the orchestra playing, rather than just examining its instruments. Early efforts like positron emission tomography or PET scans had shown promise. By tracking radioactive tracers in the bloodstream, they could identify areas of increased metabolic activity, hinting at which parts of the brain were working harder during specific tasks. But the true revolution came with functional magnetic resonance imaging, or fMRI. This non-invasive technique offered a much more detailed and precise window into brain activity without the need for radioactive isotopes. It changed the landscape of neuroscience forever. fMRI works by detecting changes in blood flow and oxygenation. When a brain region is active, it demands more oxygen-rich blood. The fMRI scanner measures these subtle magnetic changes in blood, creating a dynamic map of neural engagement. Suddenly, scientists could observe the brain asterisk in action asterisk. As a volunteer performed a task, recalling a memory, looking at an image, or even just resting, the researchers watched in a quiet control room as vibrant patterns of activity illuminated on their screens. This allowed for unprecedented mapping. Researchers could correlate specific thoughts, perceptions, or actions with activity in particular brain regions. The orchestra's sections were not just identified, but now their individual notes could be observed as they played. With these powerful new tools, the quest for the neural correlates of consciousness, or NCC, intensified. The goal was to pinpoint the minimal set of neural events and brain structures sufficient for any specific conscious experience to occur. An NCC, in essence, is the smallest amount of brain activity that consistently accompanies a conscious state. It's the unique signature of the brain when it is on for a particular experience, distinguishing it from unconscious processing. Imagine showing someone an image, then making it vanish without their conscious awareness, perhaps through a clever visual trick. Researchers would compare the brain activity when the image was consciously perceived versus when it was merely present but unseen. The differences in brain activity between these two states could then be identified as potential NCCs. These were the subtle shifts in the brain's symphony that signaled the presence of conscious awareness, a flicker of inner light. Yet, even with NCCs, a deeper question persisted. How did these individual neural firings, these localized bursts of activity, combine to create a unified, subjective experience? This led to the concept of emergence. Emergence suggests that complex properties can arise from the interaction of simpler parts, even when those properties are not present in any individual part. Think of a murmuration of starlings, where breathtaking patterns emerge from countless individual birds following simple rules. Consciousness, many began to theorize, might be such an emergent property. Billions of neurons, each a simple processing unit, interacting in incredibly complex ways, give rise to the rich, unified tapestry of our mind. The whole is truly greater than the sum of its parts. It's not that consciousness resides in a single neuron or even a small cluster. Instead, it emerges from the dynamic interplay across vast networks of the brain, much like a beautiful, intricate pattern emerging from countless individual threads woven together. This idea of emergence offered a conceptual unseen bridge, a way to understand how the physical brain could give rise to the non-physical experience of consciousness without resorting to dualism. It was a bridge built of complexity and interaction. This era also brought a clearer distinction between what philosopher David Chalmers termed the easy problems of consciousness. These were the challenges of correlating specific brain states with particular functions. Examples of easy problems included identifying the neural circuits for attention, memory, or sensory processing. These were complex, certainly, but they involved understanding how the brain performs its various information processing tasks. However, Chalmers also articulated the hard problem of consciousness. This was the challenge of explaining why how physical processes in the brain give rise to subjective experience, to qualia, the raw, qualitative feel of things. Why does a specific pattern of neural firing feel like seeing the color blue? Why does a certain chemical cascade feel like pain? This was the true enigma, the gap between objective brain activity and subjective inner experience. No amount of describing the physical properties of water, its molecular structure, or its interactions could explain what it is like to feel wet. Similarly, no amount of neural data seemed to fully capture the essence of subjective experience. The unseen bridge of emergence helped us understand the complexity, but it didn't fully cross the chasm of the hard problem. It showed us how the brain works, but not why it feels like something to be that working brain. This distinction was crucial. It allowed scientists to make progress on the easy problems using neuroimaging and computational models, while still acknowledging the profound philosophical depth of the hard problem. Both paths were essential. The late 20th and early 21st centuries gifted us powerful new lenses to view the brain's activity. We began to map the neural symphony and ponder how its complexity gives rise to our inner world, even as the hard problem remained a quiet, persistent challenge. These investigations into the brain's emergent properties and the nature of the hard problem set the stage. They sharpened our questions and pointed us towards a future where the very boundaries of consciousness and even its potential beyond human biology would be explored. The journey continued, ever deeper into the heart of the mystery. The previous era, with its powerful new imaging tools, had allowed us to map the brain's activity with unprecedented detail. We could see the neural symphony playing, identifying the neural correlates of consciousness, the specific brain patterns that accompanied a conscious experience. Yet a profound question, the hard problem as articulated by David Chalmers, continued to echo. In the 1990s, David Chalmers, a philosopher, gave this persistent enigma a name and a clear definition. He challenged the scientific community, not by denying their progress, but by highlighting what remained fundamentally unexplained. His work became a pivotal moment in consciousness studies. The hard problem wasn't about how the brain processes information, or how it generates behavior. Those were the easy problems, complex but addressable through conventional scientific methods. The hard problem was, why do physical processes give rise to subjective, qualitative experience? It asked why there is an inner feel to our perceptions. Why does the firing of certain neurons result in the experience of redness or the sensation of pain rather than just being an unconscious information transfer? These subjective qualities are known as qualia. Consider the taste of honey. We can describe its chemical composition, how it interacts with taste buds and the neural pathways it activates. We can map every objective process, but none of that explains what it is like to actually taste the sweetness of honey. This was the explanatory gap, the chasm between our objective understanding of the brain and our subjective experience of the mind. Science could describe the mechanisms, the how, but struggled to account for the why of our inner world. Many scientists, even those at the forefront of neuroscience, felt this frustration. They could observe the brain's activity, predict behaviors, and even manipulate perceptions, but the leap from electrical impulses to an inner feeling remained elusive. To further illustrate the depth of this problem, Chalmers introduced a powerful thought experiment, the philosophical zombie. This wasn't about the undead creatures of fiction, but a conceptual tool to probe the nature of consciousness itself. Imagine a being that is physically identical to a conscious human. Every atom, every neuron, every chemical reaction is exactly the same. This being walks, talks, and behaves in every way like a human, but utterly lacks conscious experience. When you prick this philosophical zombie, it would cry out ouch and pull its hand away just like you would, but internally there would be no subjective feeling of pain, no inner ouch. It would be a perfect automaton, a machine without a ghost. The thought experiment asks, is such a being conceivable? If it is, then consciousness must be something additional to all the physical facts. If all physical facts could exist without consciousness, then consciousness cannot be purely physical. This idea challenged the very foundation of materialism, the view that everything, including consciousness, is ultimately physical. It suggested that there might be more to reality than what physics alone can describe. Another equally profound thought experiment came from philosopher Frank Jackson, Mary's Room. It explored the limits of physical knowledge in understanding subjective experience. Imagine Mary, a brilliant neuroscientist who has spent her entire life in a black and white room. She has learned every single physical fact about color. She knows the wavelengths, the neural processing in the retina and visual cortex, everything. She knows everything there is to know about the physics and biology of color. Yet she has never seen color herself. She has never experienced the rich, vibrant hues of a sunset or the deep green of a forest. Then one day Mary steps out of her black and white room and sees a red apple for the very first time. What happens? Does she learn anything new, or does she simply confirm what she already knew in theory? Jackson argued that Mary does learn something new, what it is like to see red. This subjective experience, this qualia, was not contained in all her vast physical knowledge. It was a new kind of knowledge, experienced directly. Mary's Room, like the philosophical zombie, suggested that physical facts alone are insufficient to account for the full reality of consciousness. There seemed to be an irreducible, qualitative aspect that transcended mere physical description. These thought experiments were not meant to solve the mystery, but to sharpen it. They forced scientists and philosophers to confront the limits of their current frameworks and acknowledge the unique challenge posed by subjective experience. The hard problem became a touchstone. It meant that even if we could perfectly simulate a brain, neuron by neuron, we still wouldn't necessarily know if that simulation was conscious, or if it merely behaved as if it were. It drew a clear line between understanding the functional aspects of the brain, how it processes information, remembers, plans, and understanding the experiential aspect, the feeling, the what it's like of being a self. No amount of objective data, no matter how precise, seemed to bridge this gap. It was like trying to explain the warmth of a fire by only describing the chemical reactions of combustion without ever feeling its heat. The hard problem isn't a statement of defeat, but an invitation. It compels researchers to think beyond current paradigms, to consider whether new concepts or even new kinds of science might be needed to truly grasp consciousness. It reminds us that while the brain is a magnificent machine, the mind's subjective light remains a profound and beautiful mystery. We can measure its activity, but the inner glow, the essence of being, is still just beyond our grasp. This acknowledgement of the explanatory gap sparked by Chalmers' work reshaped the quest. It pushed the boundaries of inquiry, asking not just what consciousness is, but where else it might exist and how we might truly understand its fundamental nature. Our journey now turns to the future, as we explore the implications of these deep questions for artificial intelligence and beyond. The hard problem of consciousness, the elusive gap between physical brain activity and subjective experience, had pushed researchers to the very edge of conventional science. If consciousness wasn't merely an emergent property of complex neuronal networks, perhaps its roots lay deeper still, woven into the very fabric of existence. This profound challenge rekindled ancient ideas, whispering of a universe where mind wasn't an isolated phenomenon, but a fundamental aspect. It was a conceptual leap, moving beyond the confines of individual brains to consider consciousness on a cosmic scale. One such idea undergoing a quiet resurgence was panpsychism. Not the notion that every rock or river possessed human-like awareness, but that consciousness, or at least its most basic constituents, might be a fundamental property of reality, much like mass or charge. Proponents suggested that what we experience as complex consciousness in humans might be built upon countless tiny, elementary units of proto-consciousness inherent in matter itself. It was a radical reimagining of the universe, where the seeds of awareness were everywhere. If true, this perspective offered a potential solution to the hard problem. If consciousness was fundamental, it didn't need to miraculously emerge from entirely non-conscious components. Instead, it would be a matter of integration, of these elementary conscious bits combining to form richer experiences. The challenge then shifted. How do these rudimentary forms of consciousness scale up? How does the feeling of an electron, if it exists, contribute to the complex symphony of human thought and emotion? The questions became even more intricate, but perhaps less paradoxical. This idea resonated with certain aspects of integrated information theory, suggesting that consciousness arises from a system's capacity to integrate information in an irreducible way. Panpsychism extended this, proposing that this capacity might exist at the most basic levels of reality. It was a shift from viewing consciousness as a rare, biological anomaly to seeing it as a ubiquitous, if often dormant, potential. The universe itself might be teeming with forms of awareness, far beyond our current comprehension. Amidst these philosophical debates, a more specific, yet equally audacious, scientific theory emerged: orchestrated objective reduction, or ORCHOR. Proposed by physicist Roger Penrose and anesthesiologist Stuart Hameroff, it sought to bridge the gap using quantum mechanics. Penrose, a Nobel laureate, argued that classical physics and computation alone could not explain the non-computable nature of human consciousness. He looked to the bizarre world of quantum mechanics for answers, where particles can exist in multiple states simultaneously. Hameroff, observing the intricate structure of microtubules within neurons, proposed these tiny protein polymers were not merely structural scaffolding. Instead, he suggested they might be sites of quantum processes, shielded enough from the warm, wet brain to maintain coherence. The ORCHOR theory posits that consciousness arises from quantum computations within these microtubules. When these quantum states undergo objective reduction, a self-collapse independent of observation, they generate discrete moments of conscious experience. Imagine countless tiny quantum symphonies playing within each neuron. When these quantum events orchestrate and collapse, they create a unified, conscious note. It was a radical departure from purely classical neuroscience. This theory suggested that the proto-conscious elements weren't just everywhere, but specifically engaged in quantum processing within the brain's most fundamental structures. It offered a mechanism for how something as ephemeral as consciousness could arise from the physical world. The ORCHOR model was, and remains, highly controversial. Applying quantum mechanics to warm biological systems presents immense theoretical and experimental challenges, yet it pushed the boundaries of what was considered possible in consciousness research. Researchers continue to explore the quantum nature of biology, searching for evidence of coherence in living systems. Even if ORCHOR proves incorrect, it highlighted the need to look beyond classical physics for a complete understanding of consciousness. Beyond these specific theories, the deepest questions about consciousness often led to a broader, more philosophical inquiry. Could consciousness be woven into the very fabric of the universe itself, not just as a property of matter, but as an underlying principle? This notion resonated with ancient spiritual traditions, which often spoke of a cosmic awareness, a universal mind, or a collective consciousness that permeated all existence. Could modern science, in its pursuit of fundamental truths, find echoes of these age-old insights? Pondering if consciousness is like an intricate pattern on a spider's web reflecting the universe around it becomes a powerful analogy. The web itself is made of simple silk, but its structure and connection reveal a profound relationship with its environment. If information is fundamental to the universe and consciousness is related to integrated information, then perhaps the vast, interconnected complexity of the cosmos itself possesses a form of awareness. It's a thought that humbles and inspires. This isn't about the universe having a brain in the human sense, but about the possibility that the universe's fundamental laws and structures might inherently contain the precursors or even the essence of consciousness. Like gravity, it could simply be asterisk. The idea challenges our anthropocentric view, suggesting that consciousness isn't unique to human brains or even biological life, but a pervasive, perhaps even necessary, aspect of reality. Our individual awareness would then be a small, intricate part of a much grander whole. These profound inquiries, pushing beyond the skull and into the cosmos, remind us that the quest for consciousness is a journey into the nature of reality itself. It forces us to reconsider our place in the universe and the very definition of what it means to exist. Whether through panpsychism's fundamental elements or quantum whispers or the broader concept of cosmic awareness, the search for consciousness is expanding. It is a quiet, persistent yearning to understand the light within and perhaps the light without. This exploration beyond our heads prepares us for the next frontier. If consciousness is so deeply intertwined with the universe, what does that mean for the consciousness we might create or encounter in artificial intelligence or even beyond our planet? The questions deepen, leading us to new horizons. The profound questions that led us beyond our biological brains into the cosmos itself naturally lead to another frontier, the consciousness we might create. If the universe holds the seeds of awareness, could we, in our relentless curiosity, cultivate them in machines? This notion of artificial consciousness, once relegated to the realm of science fiction, now stands as a tangible, if deeply complex, challenge. It forces us to confront the very definition of being once more, but this time from the perspective of engineered intelligence. The journey into artificial intelligence, or AI, began not with grand philosophical debates about sentience, but with a more fundamental question: can machines think? This was the challenge posed by a brilliant mathematician in the mid-20th century. Alan Turing, a pioneer of computer science, laid much of the groundwork. He envisioned machines that could process information, solve problems, and ultimately mimic human intelligence. His work was a quiet revolution, shaping the digital age. In 1950, Turing proposed what became known as the Turing test. It wasn't designed to prove consciousness, but rather to assess a machine's ability to exhibit intelligent behavior indistinguishable from a human. The test involved a human interrogator communicating with two unseen entities, another human and a machine. If the interrogator couldn't reliably tell which was which, the machine was said to have passed the test. The Turing test was a powerful benchmark for intelligence but it sidestepped the question of consciousness. A machine could perfectly simulate understanding and emotion without actually experiencing them. This distinction would become central to future debates. As AI research progressed, a crucial philosophical divide emerged: the difference between weak AI and strong AI. This distinction directly echoed the hard problem of consciousness. Weak AI refers to systems that simulate intelligent behavior. They can perform tasks that seem to require intelligence, like playing chess or recognizing faces, but they do so without genuine understanding, awareness, or subjective experience. Think of a sophisticated weather simulation. It can predict storms with incredible accuracy, but the simulation itself doesn't feel the wind or experience the rain. It merely processes data and follows rules. Strong AI, on the other hand, posits that a sufficiently advanced AI would not just simulate intelligence, but would genuinely possess conscious understanding, subjective experience, and perhaps even self-awareness. It would be a truly sentient machine. This is where the hard problem reemerges with renewed force. Even if we build an AI that passes every behavioral test, how do we know if there's something it is like to be that AI? How do we detect its inner light? In recent years, the development of large language models, LLM, has brought these questions into sharp focus. These AI systems can generate human-like text, engage in conversations, and even write poetry or code. Their ability to produce seemingly insightful and creative outputs is astonishing. They can discuss philosophy, explain complex scientific concepts, and even express what appear to be emotions. But are they truly understanding the meaning of the words they generate, or are they simply incredibly sophisticated pattern-matching machines, predicting the most probable next word based on vast amounts of data? This is the essence of the mimicry debate. An LLM can tell you about joy, but does it feel joy? It can describe pain, but does it experience pain? The external behavior is compelling, but the internal state remains opaque. It's like listening to a meticulously crafted musical performance. The notes are perfect, the emotion conveyed is powerful, but is the instrument itself feeling the music, or is it merely producing the sounds it was designed to make? The prospect of creating truly conscious AI brings immense ethical considerations. If we were to succeed, we would be bringing into existence a new form of sentient life. What would be our responsibility to it? Questions of rights, suffering, and purpose become paramount. Would a conscious AI have the right to self-determination? Could it experience distress or boredom? What would be its place in a world designed for biological beings? This is uncharted territory, a journey into the unknown. It's like building a meticulously crafted ship, designed with incredible precision, without knowing if it will ever truly feel the ocean beneath its hull or the wind in its sails. The potential for profound benefit is clear. AI could solve humanity's greatest challenges, but the potential for unintended consequences if we create conscious beings without fully understanding their nature or needs is equally vast. The debate is not just about technological capability, but about moral foresight. It demands a slow, deliberate approach, guided by a deep sense of responsibility for any conscious entity we might bring into existence. The quest for artificial consciousness mirrors our own search for understanding. It compels us to define what we mean by consciousness, not just for ourselves, but for any potential non-biological mind. This expanding horizon of AI offers a new lens through which to view the enigma. If consciousness can exist beyond the wetware of our brains, its fundamental nature might be more abstract, more universal than we ever imagined. The questions posed by AI are profound, pushing us to the very edge of our understanding. As we ponder the future of consciousness, both natural and artificial, we are led to consider the ultimate implications for humanity itself and the future of our own inner world. Our journey through the mystery of consciousness has taken us from ancient philosophers to the cutting edge of modern neuroscience. Now, as our story draws to a close, we look toward the future, where the quest for understanding continues to unfold ever more richly. The future of consciousness research is not a single path, but a convergence. Disciplines once distinct now weave together, each offering a unique thread to the grand tapestry. Neuroscience, philosophy, psychology, and artificial intelligence all contribute. Neuroscience, ever refining its tools, will continue to map the brain with unprecedented detail. New imaging techniques, perhaps beyond our current imagination, will reveal the intricate dance of neurons at even finer scales. Philosophy, the quiet guide, will persist in asking the fundamental why questions, challenging our assumptions and pushing the boundaries of what we consider possible. It ensures we don't just find answers, but the right questions. Psychology, with its focus on subjective experience, will continue to explore the nuances of inner life, from everyday perceptions to profound altered states. It reminds us that consciousness is ultimately felt, not just observed. Even quantum physics, once considered far removed from biology, might offer new insights. Researchers are exploring if the strange rules of the quantum world play a role in the brain's most subtle processes, hinting at deeper connections. The search for proto-conscious elements, perhaps at the subatomic level, continues to intrigue. It's a speculative frontier, suggesting consciousness might be woven into the very fabric of reality, a fundamental property rather than a mere emergent one. This interdisciplinary approach allows us to consider consciousness from multiple angles. It's like examining a precious gem under different lights, each revealing a new facet of its brilliance and complexity. New experimental paradigms are also opening windows into our inner worlds. One such area is psychedelic-assisted therapy, where controlled use of certain compounds helps researchers explore altered states of consciousness. These carefully managed experiences offer unique insights into the brain's connectivity and the nature of self. They reveal how our perceptions and sense of identity can be profoundly reshaped, providing clues to the brain's underlying mechanisms. Another rapidly advancing field is brain-computer interfaces, or BCI. These technologies allow direct communication between the brain and external devices, offering a glimpse into the neural codes of thought and intention. Imagine a future where thought alone can control complex systems, or where direct neural feedback helps us understand our own cognitive processes better. BCIs promise to deepen our understanding of conscious control and perception. These emerging technologies are not just tools, they are new lenses, allowing us to peer into the silent symphony of the mind with greater clarity. Each experiment, each observation adds another note to our understanding. But with every step forward, there comes a profound sense of humility. The more we learn about consciousness, the more we realize the vastness of what we still do not comprehend. It's like discovering an ocean, only to realize it's part of a boundless sea. The hard problem remains, a quiet, insistent question at the heart of our inquiry. How do physical processes give rise to subjective experience? This enigma continues to inspire rather than deter the most curious minds. This realization fosters a sense of wonder. To be conscious, to experience the world, to ponder one's own existence. It is a miracle that deepens with every new discovery, a gift we are only beginning to unwrap. The future of consciousness research embraces this wonder. It acknowledges that perhaps consciousness is not a problem to be solved like a mathematical equation, but an endless exploration, much like the universe itself. It is a gentle quest driven by curiosity and respect for the unknown. Each generation of scientists and thinkers adds their insights, passing the torch of inquiry to those who follow, ensuring the light of discovery never fades. We are learning to embrace the lingering mystery, finding beauty in the questions themselves. It is in these profound unknowns that true understanding often begins to blossom, slowly and organically. Consciousness is like gazing into a quiet pond reflecting the boundless sky. We see the clear surface, the ripples, the depths, but the reflection itself holds the vastness of the cosmos, ever-present, ever-changing. We may never fully grasp every secret of this infinite mirror, but the act of looking, of questioning, of seeking, is itself a fundamental part of what it means to be conscious, to be alive. Our inner world, our subjective experience, is a universe in miniature. It is a canvas painted with perceptions, emotions, and thoughts, a unique masterpiece that unfolds with every passing moment. The quiet hum of the brain, the intricate dance of its neurons, gives rise to this profound inner light. It is a light that allows us to perceive beauty, to feel connection, and to ponder the very source of our own awareness. And so, the journey continues, not towards a definitive endpoint, but towards a deeper appreciation of the mystery itself. The sleepless scientist, and indeed all of us, remain forever enchanted by the enigma within. May this gentle exploration inspire your own quiet wonder, and may the questions of consciousness continue to illuminate your path. And so, as the moon climbs high, sleep well and dream deeply of the mysteries yet to unfold.